One thing that might have surprised you about solving linear systems is that we end up writing solution sets in terms of vectors. This is a bit of a surprise because at first glance, linear systems don't really have anything to do with vectors, but there are actually a number of features that vectors have that make them very convenient for writing down solution sets for linear systems. So let's look at those features. First of all, we're going to be working in a collection of vectors that has n entries. So in this situation, we're going to fix the number of entries and only think about the set of all vectors that have that number of entries. We usually call this Rn because each entry is a real number, right? So all of these v1 through vn, these are all real numbers. And so this collection of all of these vectors with n entries, we call Rn usually. So the nice properties that this collection has is all of these. There are actually quite a number of them. So first of all, there are two operations defined on this collection. There is addition, which, right, remember, how do you add vectors v and w like this? This is w. You just add their corresponding entries, so v1 plus w1 down to vn plus wn. And there's also an operation called scalar multiplication, where if we have a vector v1 through vn and we multiply it by a scalar in this context is just a real number. So if we multiply this by a real number, what we get is, right, just each entry times that scalar, or times that real number. So these are the two operations defined on Rn, a collection of vectors with n real entries. And what's nice about vectors is that these operations have a bunch of nice properties. So the first one is closure under addition. So if you take two vectors in Rn and add them together, you get another vector in Rn. And that one's pretty obvious. There's nothing to prove there. Commutative of addition is also another really nice property. And the reason that vector addition commutes is because when it comes right down to it, vector addition in Rn is just adding real numbers together, entry by entry. And of course, real number addition is commutative. Same thing goes for associativity. In Rn, addition is associative because entry by entry, real addition is associative. Also, in the collection Rn, there's an existence of an additive identity. This additive identity is otherwise known as the zero vector. An additive identity is just something that if you take any vector and add your identity to it, you get back the vector that you started with. And sure enough, there is such a vector in Rn. It's the vector that is just all zeros. So here, the notation that I'm using for this additive identity, this bold-faced zero, strongly indicates it has something to do with zero. And in fact, yes, it is just the vector with all zeros. So Rn does have an additive identity. Also, it has what are called additive inverses. Additive inverses are really just negatives. So for every vector in Rn, there's some other vector, so that when you add the two together, you get our additive identity. Of course, in Rn, to get, right, really what we're talking about here is negatives. And to get the negative of a vector v, you just flip all the signs on your entries, right? So no big surprise that additive inverses exist in Rn. All right, so these are all properties of vector addition. What about scalar multiplication? Well, of course, we need scalar multiplication to be closed as well. So if you take a vector in Rn and multiply it by a scalar, you get another vector in Rn. Also, scalar multiplication is sort of nice. It's associative, right, which is clear because, right, if you have two vectors here and you, whether you do this multiplication first or that multiplication first, either way you end up with SRV1 down through SRVN, so you always get the same thing. So associativity is clear. Also, multiplying, so in the real numbers, right, remember our scalars are the real numbers. In the real numbers, there is the real number 1, and the scalar product of 1 with any vector gives you that vector again. And this is clear because if you do 1 times v1 down to 1 times vn, you just get v1 through vn, right? That doesn't change anything. So scalar product with the scalar 1 gives you the same vector back. Scalar multiplication also has some nice distribution properties. So this is really about the interaction between scalar multiplication and vector addition. So scalar multiplication distributes over vector addition, and also scalar multiplication distributes over scalar addition, right? This addition right here is addition of real numbers. This addition right here is addition of vectors. So we have to say explicitly, or we should note explicitly, that that scalar multiplication distributes over both flavors of addition. So these are all, of course, the reason that both of these are true is because if you just write them out element by element or entry by entry, they come down to the distribution of real multiplication over real addition, so no big surprise there. Maybe the surprising thing is that this collection of properties is actually all we really ever use when we work with vectors, at least so far, right? In some contexts, there are some other vector operations, but at least as far as we've used them in this class so far, these are the only vector operations that we've really needed to use. And for that reason, anywhere we have a collection of things with an addition and a multiplication that satisfy all of these properties, we can treat those things as if they're vectors. And that will let us use the tools of linear algebra in a much wider context than just in the context of Rn. So that leads us to our first big definition for the course, which is what is a vector space. So a vector space is a collection of vectors and a choice of scalars, which for us is almost always going to be R, although you can do this all using complex numbers for your scalars instead of real numbers. So you need a collection of vectors, a collection of scalars, which is always going to be R, and two operations, vector addition and scalar multiplication. And these operations have to satisfy, well, that big list of operations that we noticed are satisfied in Rn. So if you have two vectors in your collection, capital V, then the sum of them has to be in capital V, so that's closure. Addition has to be commutative, associative. You have to have additive identities and additive inverses. Scalar multiplication has to be closed and associative. You have to have this scalar identity property, and scalar multiplication has to distribute over vector addition and over scalar addition. So any collection V with two operations that satisfy this big list, we will call a vector space. Okay, so a vector space, what we're going to see is a vector space is really the natural place to do linear algebra, and it's all of these properties that will make vector spaces such nice things to work with. At the moment, this big laundry list seems like it would be a big pain to check, and indeed it will be in examples, but later we'll come up with some shortcuts to help us identify vector spaces.